That's the plan for this presentation. First, I'll describe the problem, and then I'll describe a solution, and I'll justify saying that it's a great solution. So here the index origin is 0, although the ideas, the algorithms, the code, the example, and so on work in one origin with the obvious modifications. So the problem is to find x index of y, where x and or y are floats, meaning real or complex, and the major cells have more than one element. So in other words, x can be a matrix, or a three-dimensional array, or n-dimensional array. And in the case of matrices, I would be finding the occurrences of rows of y in rows of x. And the comparison tolerance is not 0. In other words, we're not using exact comparisons here. It's a problem I've worked on for more than 20 years, and but didn't have a good solution until now. For this problem, the best solution is to not have the problem at all. It's no joke. If in your application you can get away with using exact comparison, namely by setting quad CT to 0, you should do that. So you as an APL user can have that choice. But we as APL implementers cannot have that choice. Now, it's a 20-year-old problem, so what made us look at it again? We were motivated to revisit this problem because there was a bug in tolerant unique, which I will talk about tomorrow. But this is a key step in solving that bug. Oh, there's no bug in x index of y, but it's slow. So the problem here is that it's slow. So F generates a real matrix with omega rows and alpha columns, and then does a timing on it. Okay, so here is generating 3-column matrices with 1,000, 2,000, 4,000, 8,000, 16,000, so on, number of rows, doing timings on them, and then we want to look at the growth pattern in the time, okay? So these times show that the current implementation is order n squared, because when the argument size doubles, because we're doubling the number of rows each time, the time quadruples. So n doesn't have to be very large before you get into real problems with response time. In contrast, if you do timings on vectors or one-column matrix on the same number of major cells, the time roughly doubles when the argument size doubles. So for vectors or one-column matrices, the current implementation is linear. And we would like this to be linear as well. And the last number on the slide shows that for 32,000 rows, the vector case is faster than the 3 columns case by a factor of 2600. Okay, so now I'm going to describe steps toward a solution. So cluster is a function that sorts the argument. So in the when the argument is a real vector, you can sort it so that tolerantly equal items are contiguous. So this cluster function does it, and it uses the new interval index primitive. It's amazing how notation works, because the ink is barely dry on interval index, and we're using it in an essential way to solve a 20-year-old problem. There's a bit of subtlety in here, because it's doing sorting, and sorting uses exact comparison, so it's unavoidable. Sorting is using exact comparisons. And in computing the interval endpoints, it's using tolerant comparisons. Again, unavoidable when we're solving this problem. Okay, so an example using integers, which makes the point equally well. So I've shown x in red and y in blue, and I have applied cluster to the concatenation of x and y. So the indices for x are, the interval indices for x are, or cluster indices for red, for x are red, and the cluster indices for y are blue. And then a combination that works like ham and eggs, or what are some other pairings that work well? Peanut butter and milk. No. Key and interval index work really well together. So I've computed cluster indices using interval index, and then applying key to the result of interval index, getting, indices into the original x and y. And in each cluster, the red are indices from x, or indices into x, and the blue are indices into y. And you notice that it's very possible for there to be indices for x only in a cluster, and also indices into y only in a cluster. Okay? Now, if the arguments are multiple flows, in other words, have more than one element in the major cell, you cannot sort them so that tolerantly equal items are contiguous. And this is one example of it. And here's where real genius comes in. J. Fode made the key observation that you can cluster the columns of X independently of each other. So that's what this is doing. So X is a 3-column matrix, real matrix, and I'm clustering the columns by clustering the rows independently, and then transposing back. And K is a integer matrix with small range integers, actually, and you can use it as as the keys to the key operator on X. Okay? Now these numbers you see are not exactly equal, so I've formatted it or displayed it using a plus if it's slightly bigger than 1. Okay, so you see that these are only tolerantly equal within a cluster. Okay. Now we want to work with the cluster indices rather than the data elements themselves, so we can use it in a monadic case of key. On k iota k. Okay, and these are clusters of rows in X. Okay. So putting all the ideas together, we have this operator. Now the key thing to know about this slide, the most significant point is actually the name of the operator, hash. I mean, it took me a while to recognize that what's happening is hashing, and the cluster calculation is the hashing function. In this case, alpha alpha. So let's go into it in detail. So here, the hash function I will use is what I discussed before. Use cluster, the function cluster independently on the columns of the argument, getting an integer matrix, and then doing a selfie, k iota k, on it, to get an integer value for the hash function. Okay? So inside the hash operator, it applies alpha alpha, the hashing function, to alpha catenated with omega, and then using key to get the hash indices. Okay? And then once I get the cluster indices, I apply an anonymous function to each cluster. Okay. This is an example of what Aaron talked about this morning, that you don't always have to name the function, because this function is anonymous. So inside this anonymous function, the index p are indices into capital X, which is the original left argument, and the name q denotes John denotes indices into capital Y, the original right argument. And then once I get those, I still apply the original order n square index of to those two parts. And the way hashing works is that it's okay to apply an order n square computation on these two parts, because hopefully your hashing function is good enough that these two parts are small. Doing the index off and then indexing back to the original indices for X, and then assigning it to the result. Okay? So this little benchmark shows that on matrices with 1e4 columns, 1e4 rows and 3 columns, this APL model is faster than the current implementation by a factor of 16. Yeah. Okay. The most pleasing part about this function, or this operator, sorry, is that it compares well with a function we wrote in 2010. It's less general because it computes x iota y on real vectors. So, column. Sometimes it's possible for old geezers to learn new tricks. So this one is from 2010, and this one is from this year. Now there are different ways of judging code. Aaron uses the amount of money you want to bet on this, right? And John wants denotational rather than some other thing. I have a different criteria. Mine is, I call it monument quality code. Now we're not quite there yet, but we're getting closer. So we were quite pleased about this. And then try to apply it to the complex case. Now, for complex arguments, you can't sort them in a way that tolerantly equal major cells are adjacent to each other. Not just because currently gray up doesn't accept complex numbers, but because it's inherently not possible. But we can sort on the magnitudes of the real numbers, of the complex numbers, which are real, of course, and then cluster on those. So this will be our hash function, hz, and then computes the same answers as the current primitive, and it's faster than the current C implementation. X iota y is currently implemented in C, and here we have the APL model, and it's faster by a factor of 40 on real arguments. On complex arguments. So, as I said, we were quite pleased about this until it ran afoul of some QA that we wrote in 2010. And the repro for the problem that the QA found is as follows. So A is a number with real part 1 and complex and imaginary part 1 plus quad CT. And B is a complex number with real part 1 plus quad CT and imaginary part 1 plus quad CT times 2. And X and Y are vectors of A and B randomly distributed. So A and B are tolerantly equal. So X iota Y should be all zeros. But the APL model gives the wrong answer. So what's the problem? Well, the problem comes down to the fact that A is equal to B, but the magnitude of A is not equal to the magnitude of B. And if you do a little bit of algebra based on the definition of tolerant equality, you get this result, where the magnitude of the difference in the magnitudes is greater than the magnitude of the difference in the original numbers. But that contradicts the triangle inequality, which was proven by Euclid more than 2,000 years ago. Don't you just hate it when the QA contradicts proven facts? The problem, of course, is floating point arithmetic. Because, okay, so here's a little geometric proof of the triangle inequality. The difference in the two numbers, the magnitude of the difference in the two numbers is the thing in red, and the magnitude of the difference in the magnitudes of the thing in yellow, and the calculations show that the yellow is longer than the red, which is supposed to be impossible. So welcome to the wonderful world of floating point calculations. Okay, I better hurry it up. So when you actually do the calculation, you see that when you use 64-bit floating point, the first number is less than the second number, which is supposed to be impossible. So I said, that's not possible. So I did some calculations in J using extended precision arithmetic, using 120 decimal places in the calculation and displaying 40 decimal places, and show that no, it is actually, math does hold if you use enough precision in the calculations, but it only shows up in the 28th decimal place. Fortunately, there's an easy trick to get around this, because we can't really afford to do the calculations using 120 decimal places, right? Or other heroic methods like that. And the trick is to use twice the tolerance when we're doing the clustering. So the hash function, instead of just this part in the braces here, we modify it, or we derive a different hash function using twice the tolerance, and then we get the right answer again. Now, is twice the tolerance enough? Well, we don't yet have a proof, but we do have empirical evidence, because 1.005 times the tolerance is still enough, but 1.004 times the tolerance is not enough for this example, for this data. So the hash APL, yeah, Morton is shaking his head, because we have something for which we have a proof but fails the QA, right? And here we don't yet have a proof, but it works. So, we have implemented this in version 17, and we did some benchmark compared to the version 16 for various number of major cells. And the timing, of course, depends on the number of clusters. If you're extremely unlucky, or you have data designed to defeat the clustering, then it takes more time because you did the clustering for nothing. But it's still, you can see that the trend is looking good, because I managed to speed up the quadratic search as well. But anyway, if you're not really unlucky, then you get these good-looking trends. It's linear. We have a linear solution. So this is the factor in the real case for 64,000 rows, and the factor in the complex case for 64,000 rows again. That's it. Any questions?
This is more out of curiosity than anything else. When you increased the tolerance there, would that have the effect of putting more numbers into each cluster?
Yes.
And,
yes, that's right.
And so the question is then, what effect does that have on performance, because you're doing these iotas on larger sets, which are still hopefully pretty small?
Yeah, it depends on the data, as you know. But it's okay, because that's the way hashing works. If you hash more things together into the same hash, you get not as good performance, but it still gives correct answers. Whereas the other way gives you wrong answers, which is not a choice. Yeah.
Okay, anyone else?
Yeah.
No? Okay, thank you, Roger.
Thank you.